Thank you. So my name is Marcel Fourné, and I'm currently working for the Max Planck Institute for Security and Privacy. That's the one in Bochum, Germany. And you see, I've got a lot of co-authors here, and I won't name all their contributions. But in the end, you know, you can get the paper and you get in contact with us. So I'm going to talk about reproducible builds and why they are important. And first, I'm going to introduce an attack. Huh? Clicker doesn't work.
Take a look. Is this the PDF being too big? I think just.
Yeah. So there was Ken Thompson, you might know him, and in 1984 he won Turing Award, and he introduced in his lecture for the Turing Award an attack called the trusting trust attack. And it's an attack that attacks the relation between the compiler and the compiled binary. Like, you've got your compiler C and your source code for the compiler S. And the backdoor, which he introduced is, well, you modify the compiler to include a backdoor into every program that gets compiled with it. And then you compile that compiler. You get the modified source code with a backdoor, which is S prime. You compile it to binary. You get the backdoor compiler C prime. Yeah. And then you publish the unmodified source code S, and you publish the compiled and backdoored compiler C prime. And in the end, you end with a undetectable backdoor because you can look at the unmodified source code and you can compile it again. And you will still get the backdoored compiler binary. And you get, every binary gets backdoored if you compile it. But every source code will be clean. So you won't know that everything you will compile will be backdoored. So Ken Thompson said, well, to what extent should one trust the statement that a program is free of Trojan horses? Perhaps it's more important to trust the people who wrote the software. And this was true until, well, there was this paper and a dissertation by David A. Wheeler called Countering Trusting Trust Through Diverse Double Compiling. This is the defense for the trusting trust attack. And you need to get multiple compiler binaries to agree on a compiled binary program. The results, if they are bit by bit equal, like if you have one trusted compiler, then you know all the other compilers can be trusted as well because their results are the same. And it's much harder to build a backdoor that is stable across different compilers. And in the end, statistics do win out. But there is one requirement. The compilers need to agree by default. Without this, you won't have the equal results by the compilers. And the problem is, currently, most don't. And it's not just different compilers like GCC and Clang giving different results, but also the same compiler in the same environment for the same source code giving different results. Think of profile-guided optimizations. Now, what we need to get this defense to work are reproducible builds. This is getting bit by bit reproducible artifacts by default. And there's different technical problems, like build timestamps being included in binaries, build paths, file system ordering, archive metadata, randomness, uninitialized memory in binaries, all these things. So we need to make the tools which build our software make things more reproducible. And we need to build CI to check how far open source code, which is out there, is being built reproducibly. And this has been a community effort for quite some years. Publicly, Bitcoin project did this in 2011. Tor project did this in 2013. This coincides with the Snowden revelations. And the Debian project, there have been traces on the mailing lists in 2000, explicitly in 2007, but really in earnest since 2013. This is also when the reproduciblebuilds.org project was founded. And currently, just to give you an update on how far we are, the Debian bookworm AMD64 is 96.2% reproducibly built. And Arch Linux Core, 90.2%. And you can check this yourself. This is direct results from the CI. So what did we do? Well, we did a qualitative interview study, and we recruited people from the reproduciblebuilds.org mailing list and talked with them about our 3 main research questions. And those are, what are the motivations for getting into reproducible builds, for working on this problem, for changing things? What are your experiences and what were the challenges on this? And what are the most commonly encountered obstacles, but also facilitators on helping with those problems? We contacted 110 people by email, and 24 people participated, but not all interviews were just over the internet, because we also were at the Reproducible Builds Summit last year, which is 2022, in Venice, and 6 of the interviews we did in person. We also participated in the summit, of course. You can see as a small overview of our participants, it's not just developers. We also have one CEO of a company. We've got an advisor on different projects. It's all over the place. Industry, open source projects, activist projects. You can look into the paper, and it's quite a diverse background. So what are the results? What did we find out? Well, there are reasons for and against working on reproducible builds. The reasons for working on it, by the largest amount, is people want to have programs which work like expected, deterministic programs, programs that work like you programmed them to do. This is, for them, also an aspect of build quality, which is really hard to define. But if people see something that invalidates their assumptions, people get motivated to work a lot on this. Also, since I mentioned the Snowden revelations, there's an aspect of developer security against coercion, or maybe honest mistakes. There was one occasion where a developer included a private key into a repository, and the private key was introduced into a build, and the difference was found by reproducible builds because there was a binary difference that was only explainable by, well, there was the new key introduced, and that got included. In the end, we do not want to have blind trust in the build artifacts. We want to have a provably secure supply chain security. Also, if you're more interested in cost savings, like for companies, you can do most efficient caching of build artifacts if the build artifacts themselves are bit by bit identical after each build. Then you only need to build them once, cache the results, presto. But there are also reasons against working in this. And a lot of it is repetitive work, because you need to really get all the packages to build reproducibly. And if you want to upstream your work, there's a lot of interaction with upstream projects. The open source community is kind of good in this, but it might be harder for companies. And many organizations, including open source projects, do have like very mixed organizational buy-in. And even if you get something to build reproducibly, bit by bit reproducibly, then if you change the environment, things might still change, and then you've got to fix it again. So what are the main obstacles which make this harder? Well, first of all, lack of good communication. If a project doesn't answer, you have to wait. Sparse documentation. This is because there are only few people working on this. And there are many common technical problems. Most of them are build directory name inclusion, which happens quite often for the main compilers. And whole ecosystems have embedded cryptographic signatures in files. And of course, the compilers themselves and the tool chains are very complex. But if you change them and fix them, then you can probably fix a lot of packages at once. And the most helpful factors were self-effective participants who did not need interaction to work on the problem. They could start themselves. They could build the whole CI. And good interaction between the developers and other projects, upstream projects, downstream projects, really helped. Also, a lot of patience. And they built some good tooling, Diffoscope, which is known in not just the reproducible builds.org community, and ReproTest, which is used for some CIs which test all of this. But still, the community is quite small, and there's a lot of cleanup for technical debt, which we, I assume, all know. So the biggest regret that was mentioned was missing outreach. And there's some real-world impact. You might have heard of software bill of materials. Well, this was also mentioned by President Biden in the executive order on improving the nation's cybersecurity, on the order of $100 billion. And in the EU, there's liability laws being discussed, which might harm free and libre open source projects. In industry, there's signing commits. You might have heard of SIGSTAR, which is a ledger that gets audited by some trusted third parties. The OpenSSF scorecard, which is for compliance efforts. And the Floss community itself, well, they're working on building things reproducibly, on bootstrapping builds from very tiny binaries, and making the diverse double compiling a community effort that users can inspect. So what now? We've got some recommendations. First, we need industry buy-in and empowerment of their engineers, which are the people which can fix this. And a Floss community should have secure by defaults, which is make everything being built reproducibly by default and make an issue if it isn't. And we say, we as a security community should also look into things which might change the binaries that we need to trust. And governments mandating liability, well, that liability should only be for last level commercial for-profit entities and not Floss projects. This might harm the whole industry if this gets worse. So what more research do we need to do? Well, how can we make the benefits of reproducible builds visible and usable by end users? How can we make a distributed, trusted, and distribution agnostic, but still integrated DDC process? And how can we make it interactable for users? Usable authentication, which developers might accept, how can we do that? And the whole chain of dependencies and frameworks, all of this is a lot of work. So in the end, what did we find? Well, we find there are varied motivations. Most people want deterministic software. And this helps developers and the supply chain security in general, while reducing the costs for companies and OSS projects as well. We need organizational buy-in, but we got good upstream interaction. And build directory name inclusion and cryptographic signatures are the biggest problems which hinder, but patience and good social interactions are the biggest things which help reproducible builds. Do you have any questions?
Awesome. Thank you, Marcel, for the awesome talk. Any questions? If you have questions, please stand. I'll just give you my microphone.
Do you think that the open source or community would be open to have SBOM like a requirement where they have to disclose everything?
There is some discussion about this. Some people are open about it, but you won't get everybody on board on this. You might get some bigger projects, and you might get very many projects overall, but you can't force everybody to join on this, because still many people are doing this for a hobby. But if you do this by default, and if you have a clear track record, like, for example, the Debian project does a lot of this in compliance, legal compliance, then you could get this like for most things.
Thank you.
So, do you believe SBOM can make a viable contribution? I think it's a pile of shit myself. So. And I say that in a technical sense.
Yeah.
I mean, people cannot produce the same SBOM, and if it doesn't do that, and even then, the operational concept of how to actually do something beneficial with it once you have it is another thing. This is a 10 to 15-year project with an uncertain future. I can say this because I'm close enough to retirement, I don't care, but will you speculate a little bit on SBOM, please?
Yes, I can do that. SBOM is no final thing that will fix all problems. It only gives an insight into what is included in artifacts, and SBOMs can be wrong. They can be forged. If you want to know what is included in the thing you're actually executing, you want to have the whole chain that got into your artifact. SBOM is one way of documenting that, but we all know that documentation can be outdated, can be quite factually wrong. And that way, SBOM is better than not doing anything, because currently we don't know what is being executed. We have the binaries, but what gets in our binaries? There could be something hidden in there, something we can't see the source code of, or we can't trust the source code of. So in the end, we want to have something that we can rebuild, and SBOMs, I think personally, should be automatically generated during build, always. There's some projects like in Debian doing not SBOMs per se, but a different format. There's a project that converts the Debian format to SBOM right now. This gets generated as .build info files during build. And this is done by default. So you have some information during builds which projects were used. But you need to do this on an ecosystem level. And still, if you're doing something maliciously, this gives you no guarantees. You need to do this yourself. And you need to compare the results.
Awesome. Thank you very much. Thank you, Marcel, again for the talk. And then